According to the National Electrical Code, the minimum wire size for a 1600 amp switchboard is 750 mcm or 1000 circular mils. The use of 600 mcm copper wire is not sufficient to meet the code requirements. Let's discuss conduit capacity. For 5 parallel 750 mcm THHN cables, the area is 4.27 square inches. For 5 parallel 750 mcm XP cables, the area is 4.55 square inches. Now let's consider 5 4-inch PVC conduits. The area of each conduit is 12.57 square inches, so 5 multiplied by 12.57 square inches equals 62.85 square inches. This conduit capacity is sufficient to accommodate the cables without exceeding their allowable fill percentage. Now let's look at ampacity calculations. The motor loads include 3 150 horsepower motors, 2 100 horsepower motors, 2 50 horsepower motors, and 5 20 horsepower motors. This results in a total of 700 horsepower. Using a service factor of 1.15, 700 horsepower multiplied by 1.15 equals 805 horsepower. Assuming a 480 volts, 3-phase system, the ampacity is calculated as 805 horsepower divided by 0.746 kilowatts per horsepower, divided by 480 volts, and then multiplied by the square root of 3. This equals approximately 1083 amps. Based on these calculations, the following wire and conduit configurations meet the NEC code requirements for a 1600 amp switchboard with the specified motor loads. The recommended wire size is 5 parallel 750 mcm THHN or XP cables. The recommended conduit configuration is 5 4-inch PVC conduits. The calculated ampacity is 1083 amps. Let's break this down further. The National Electrical Code, or NEC, sets the standard for electrical safety in the United States. Adhering to the NEC is crucial to ensure the safe and reliable operation of electrical systems. When sizing conductors for a 1600 amp switchboard, several factors must be considered, including the ampacity of the conductors, the ambient temperature, and the number of conductors in a raceway or cable. The NEC provides tables and guidelines to assist in determining the appropriate conductor size for various applications. The term mcm stands for 1000 circular mils, which is a unit of measurement for the cross-sectional area of a conductor. A larger mcm value indicates a larger conductor size, which can carry more current. The NEC specifies the minimum conductor size for different ampacity ratings to prevent overheating and ensure safe operation. THHN and XP are common insulation types for conductors used in electrical systems. THHN stands for thermoplastic high heat resistant nylon coated, while XP stands for cross-linked polyethylene. These insulation types offer different temperature ratings and resistance to environmental factors. When selecting conductors, it's important to choose an insulation type that is suitable for the intended application and environmental conditions. Conduit is a protective tube or raceway used to enclose and protect electrical conductors. The NEC specifies the types of conduit that are permitted for different applications, as well as the maximum number of conductors that can be installed in a conduit of a given size. Proper conduit fill is essential to prevent overheating and ensure easy access for maintenance and repairs. The ampacity of a conductor is the maximum amount of current that it can carry continuously without exceeding its temperature rating. The NEC provides ampacity tables that list the ampacity of different conductor sizes and insulation types under various conditions. When calculating the ampacity of conductors for motor loads, it's important to consider the motor's horsepower rating, voltage, and service factor. The service factor is a multiplier that accounts for the motor's ability to handle overload conditions. The NEC requires that conductors be sized to handle the motor's full load current, plus an additional amount to account for the service factor. Parallel conductors are often used in high current applications to increase the ampacity of the circuit. When using parallel conductors, it's important to ensure that all conductors are of the same size, material, and insulation type. The NEC also requires that parallel conductors be installed in the same raceway or cable to ensure that they share the current equally. In this specific scenario, the initial question involved determining whether 5 parallel 750 mcm THHN or XPLE cables would meet the NEC code requirements for 1600 amp switchboard. The analysis confirmed that this configuration is indeed code compliant, provided that the conduit capacity is sufficient and the ampacity calculations are accurate. The use of 600 mcm copper wire was deemed insufficient, as it does not meet the minimum ampacity requirements for a 1600 amp switchboard. Let's delve into the specific NEC articles that are relevant to this situation. NEC Article 310 covers conductors for general wiring. It provides detailed information on conductor ampacity, temperature limitations, and installation requirements. NEC Article 310.15 specifically addresses ampacity calculation and adjustment factors. It outlines the procedures for determining the ampacity of conductors based on factors such as ambient temperature, number of conductors in a raceway, and type of insulation. NEC Article 310.16 provides ampacity tables for conductors rated 0 to 2000 volts. These tables list the ampacity of different conductor sizes and insulation types under various conditions. NEC Article 310.20 covers conductor overcurrent protection. It requires that conductors be protected against overcurrent by fuses or circuit breakers that are sized appropriately for the conductor's ampacity. NEC Article 310.3 addresses the use of parallel conductors. It outlines the requirements for installing parallel conductors, including the need for equal size, material, and insulation type. NEC Article 314 covers outlet boxes, device boxes, and pull boxes. It provides information on the size and installation of boxes to ensure that they can accommodate the conductors and devices installed within them. NEC Article 344 covers rigid metal conduit. It specifies the types of rigid metal conduit that are permitted for different applications, as well as the installation requirements for rigid metal conduit systems. NEC Article 352 covers rigid polyvinyl chloride conduit, or PVC. It specifies the types of PVC conduit that are permitted for different applications, as well as the installation requirements for PVC conduit systems. NEC Article 430 covers motors, motor circuits, and controllers. It provides detailed information on the sizing of conductors, overcurrent protection, and control equipment for motor loads. NEC Table 430.250 provides full load current ratings for three-phase alternating current motors. This table is used to determine the full load current of motors based on their horsepower rating and voltage. NEC Table 310.15b16 provides allowable ampacities of insulated conductors rated up to and including 2000 volts, 60 degrees Celsius through 90 degrees Celsius in free air. This table is essential for determining the ampacity of conductors based on their insulation type and temperature rating. NEC Table 310.15b3 provides adjustment factors for ambient temperature. This table is used to adjust the ampacity of conductors when the ambient temperature is higher or lower than the temperature rating of the conductor. NEC Table 310.15b3 also provides adjustment factors for the number of current-carrying conductors in a raceway or cable. This table is used to adjust the ampacity of conductors when multiple conductors are installed in the same raceway or cable. In summary, the NEC provides a comprehensive set of rules and guidelines for the safe and reliable installation of electrical systems. When sizing conductors for a 1600 amp switchboard, it's crucial to consult the NEC and follow its requirements carefully. Failure to comply with the NEC can result in overheating, equipment damage, and even electrical fires. Remember that the 750 and CNTHHN or XPLE cables in parallel, along with the appropriate conduit configuration, are code compliant for the described scenario, given the specific motor loads and other parameters mentioned. Always consult the latest edition of the NEC and work with qualified electrical professionals to ensure that all electrical installations are safe and code compliant. Furthermore, let's consider the importance of proper termination and connection methods. The NEC requires that conductors be terminated and connected in a manner that ensures a reliable and secure connection. This includes using approved connectors and terminals that are properly sized for the conductor. Proper termination and connection methods are essential to prevent overheating, arcing, and other electrical hazards. In addition to conductor sizing and termination, it's also important to consider the voltage drop in the circuit. Voltage drop occurs when the voltage of the load is lower than the voltage of the source. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC provides guidelines for calculating voltage drop and specifies the maximum allowable voltage drop for different types of circuits. To minimize voltage drop, it's important to use conductors that are large enough to carry the required current over the distance involved. It's also important to minimize the length of the circuit and to use proper wiring techniques. Another important consideration is the coordination of overcurrent protection devices. Overcurrent protection devices, such as fuses and circuit breakers, are designed to protect conductors and equipment from overloads and short circuits. The NEC requires that overcurrent protection devices be coordinated to ensure that the smallest overcurrent device trips first, minimizing the extent of the outage. Proper coordination of overcurrent protection devices requires careful selection and settings of the devices. It's also important to perform regular testing and maintenance of overcurrent protection devices to ensure that they are functioning properly. In addition to the technical aspects of conductor sizing and installation, it's also important to consider the safety aspects of working with electricity. Electricity can be dangerous, and it's essential to follow safe work practices to prevent electrical shock and other injuries. Some important safety practices include energizing circuits before working on them, using insulated tools and equipment, and wearing appropriate personal protective equipment, such as gloves and safety glasses. It's also important to be aware of the potential hazards associated with working in confined spaces and to follow proper lockout/tagout procedures to prevent accidental energization of circuits. Furthermore, consider the impact of harmonics on electrical systems. Harmonics are distortions of the sinusoidal waveform of alternating current. They can be caused by nonlinear loads, such as electronic equipment and variable frequency drives. Harmonics can cause a variety of problems, including overheating of conductors and equipment, malfunctioning of electronic devices, and increased energy consumption. To mitigate the effects of harmonics, it's important to use harmonic filters and to properly size conductors and equipment to handle the harmonic currents. Additionally, regular power quality monitoring can help to identify and address harmonic problems. Let's also discuss the importance of grounding and bonding. Grounding is the connection of electrical equipment and circuits to the earth. Bonding is the connection of metallic parts of an electrical system to create a low impedance path for fault current. Grounding and bonding are essential for preventing electrical shock and for ensuring the proper operation of overcurrent protection devices. The NEC provides detailed requirements for grounding and bonding, including the size and type of grounding conductors, the location of grounding electrodes, and the methods for bonding metallic parts. Proper grounding and bonding practices are critical for the safety and reliability of electrical systems. Finally, let's consider the importance of documentation and record keeping. It's important to maintain accurate records of all electrical installations, including conductor sizes, conduit types, overcurrent protection device ratings, and grounding and bonding arrangements. These records can be used for future reference and for troubleshooting purposes. It's also important to document any changes or modifications to the electrical system. Proper documentation and record keeping are essential for the safe and efficient operation of electrical systems. Remember to always consult the latest edition of the NEC and to work with qualified electrical professionals to ensure that all electrical installations are safe and code compliant. The information provided here is intended for educational purposes only and should not be considered a substitute for professional advice. In addition to the points already covered, let's address the specific application of the 1600 amp switchboard in relation to the motor loads. When dealing with multiple motors, the NEC requires specific calculations to determine the appropriate conductor size and overcurrent protection. The largest motor is treated differently than the other motors. The conductors supplying the group of motors must have an ampacity of not less than 125% of the full load current rating of the highest rated motor, plus the sum of the full load current ratings of all other motors in the group. This ensures that the conductors are adequately sized to handle the starting current of the largest motor, as well as the combined running current of all the motors. The overcurrent protection for the motor circuit must also be sized appropriately. The NEC provides tables and guidelines for selecting the correct overcurrent protection device based on the motor's horsepower rating, voltage, and code letter. The overcurrent protection device must be capable of interrupting the motor's starting current, as well as providing protection against overloads and short circuits. Furthermore, the type of motor starter used can also affect the conductor sizing and overcurrent protection requirements. Different types of motor starters, such as across-the-line starters, reduced voltage starters, and variable frequency drives, have different starting current characteristics. The NEC requires that the conductor size and overcurrent protection be selected based on the specific type of motor starter used. In the specific scenario described, the motor loads include a mix of different horsepower ratings. To determine the appropriate conductor size, it's necessary to first identify the highest rated motor, which in this case is the 150 horsepower motor. Then, the full load current rating of the 150 horsepower motor must be multiplied by 125%. Finally, the result must be added to the sum of the full load current ratings of all the other motors in a group. This calculation will determine the minimum ampacity required for the conductor supplying the group of motors. In addition to the conductor sizing, it's also important to consider the ambient temperature and the number of conductors in a raceway. The NEC provides adjustment factors that must be applied to the conductor ampacity to account for these factors. The adjustment factors for ambient temperature are based on the temperature rating of the conductor insulation. The adjustment factors for the number of conductors in a raceway are based on the directing factors specified in the NEC. Once the conductor ampacity has been adjusted for ambient temperature and the number of conductors in a raceway, the conductor size can be selected based on the adjusted ampacity. It's important to select a conductor size that is large enough to handle the adjusted ampacity, as well as any future increases in load. In summary, the conductor sizing and overcurrent protection for 1600 amp switchboards supplying multiple motors must be carefully calculated to ensure that the system is safe and reliable. The NEC provides detailed guidelines and requirements for these calculations. It's important to consult the NEC and to work with qualified electrical professionals to ensure that all electrical installations are code compliant.